speaker is Arkady Pikovsky with and непомнящий with the top cause in coupled heteroclinic cycles and its piecewise linear description. Arkady, we don't.
Oh, yeah, do you see my screen? Yes.
Yes. Yes. We see your screen.
I can start. So this will be a rather numerical presentation of what project Vitalik Nepomniachtchi from Technion about chaos and coupled heteroclinic cycles. So the stable heteroclinic cycle is an object probably first introduced in 1975 by May Leonard as some kind of generalization of Lotka-Volterra competition of species. And here it is competition of 3 species, but organized in such a way that they are cyclic, like in this popular game of scissors, which beat paper, paper which beat rock, beats rock, and rock which beats scissors. So there are 3 variables should be, and so the condition of that one beats another is in this restriction on parameters. So there is one parameter alpha which is larger than 1, parameter beta which is less than 1, and this sum should be also larger than 2. And in this case, so this equation realizes this stable heteroclinic cycle, which in the projection on 3-dimensional space looks like connections here of the 1-dimensional unstable manifolds of 3 steady states, where one of these species does exist, so one or another or the third one, and they are heteroclinic cycle connects the steady states, and formally the period for this cycle is infinite. But if you start a trajectory, you will see so how it approaches the cycle, so that period really grows. So for each rotation, a period of next rotation is some factor multiplied period of previous rotation, so this period grows exponentially with the number of rotations. And if you look on growth rates, so these are these quantities in these brackets, so they are, so to say here, nearly constants. So there are long exponential pieces with some switchings at this point. So this is how stable heteroclinic cycle works. And but let us, for the future, it will be more suitable to use new coordinates to resolve singularities. So the cycle spends a lot of time close to 0 and to 1, but it is better to resolve it introducing such a variable x and correspondingly y and z, so that states close to 0, they correspond to large negative values of x, and states close to 1 corresponds to large positive value of x. And so you can rewrite equations in these variables, and the attractor, or heteroclinic cycle in these variables looks like this. So there are oscillations with growing amplitude because so this trajectory approaches this heteroclinic cycle, and this means so that values, very large positive values and very large negative values are now possible. So it's a just representation which resolves states close to 1 and states close to 0, which are here negative, large negative values. Okay, so this is one heteroclinic cycle, and now what we do, we couple 2 such cycles, but to make things non-trivial, we take them rotating in opposite directions. So imagine that you have one cycle which goes usually like rock, this is paper, but in another cycle, so it rotates in opposite direction. So this is possible. If the only thing what you need is to replace in second cycle this parameters beta and alpha, because they essentially give you the direction of rotation. So if you replace them, so instead of alpha, you put here beta, and here instead of beta, you put here alpha, you will have two cycles, 1 and 2 rotating in opposite directions. And then we will couple them diffusively so that now variables, corresponding variables, you tend to be close to each other due to this coupling. Idea is so that because of high sensitivity of heteroclinic cycle, or altogether trajectories which are close to these saddle points, so the values for this D could be very small, and below we also replace this coupling constant with this, take it e to the power minus q, because it is q large will mean so that it is very weak coupling. And now let us look on the bifurcation diagram. So it is what you can do for this 6-dimensional system. We have chosen some parameters, alpha and beta. And here, so take this coupling strength Q as the basic parameter. So this area, large Q, corresponds to a very weak coupling. And small q, it is large coupling. And this is a bifurcation diagram in Poincare map. So 1 point means so that there is a just periodic orbit, and here it is some period doubling, so there is some symmetry breaking. There are 2 attractors here, symmetric because system has a lot of symmetries. And then you see here there is some period doubling cascade. And so then you observe chaos, essentially 2 types of chaos here. And the main message of this picture is so that you typically observe chaos, except maybe for some periodic windows, which are quite narrow here, really for extremely small coupling. So that coupling is small, and here chaos is persistent. Yeah, so this is, so very weak coupling immediately gives you chaos, contrary to usual situations when you start with coupled limit cycle oscillators, and then you need strong coupling to have chaotic behavior. Here coupling appears for very small values, chaos appears for very small values of coupling. And so this is the main, how to say, numerical message. And the rest of my talk, which will be not too long because I want to catch the schedule, is about how we can understand this picture more or less, so to say, to some extent analytically. And to this end, so we build what we call piecewise constant model for the heteroclinic cycle. So if, again, so I write my equation, so in these variables, which are x, y, z, which are logarithms of original variables, and in these variables, so the right-hand side looks like this. So you see here, there are exponential functions. And if you look on the right-hand side, so especially in the denominator, it's for those who studied physics, so it's, you see it resembles what is called in physics Fermi distribution, which so has the following forms. So function of energy, which has a particular limit, which is very simple, is if this parameter temperature goes to 0. So in this limit, so this function takes 2 values, 0 and 1. It is essentially a step function. And the idea is so that maybe we can also represent our right-hand sides, also some make approximated them with some kind step function. Although we don't have a small parameter here, we just have parameter x. But we can consider, we have seen so that close to heteroclinic cycle, this variable x take very large values, some maybe 100 or 1,000, and negative values, say minus 100, minus 1,000. So maybe if we consider these variables as themselves or their scale as large, so we can make this approximation and represent functions containing these exponents as a piecewise constant functions.
Can you show video?
Sorry?
We don't see you. Did not see you.
Just a moment. So
I'm sorry.
Oh, now you see?
Okay.
Okay, sorry for this. So it is, I'm alive, yeah. Okay, so the idea is, so again, so to represent, so the smooth function, to approximate it with a piecewise constant one. And so we typically have here this ratio. And if we do this approximation, so we have for this ratio, essentially 3 possible values, depending on the relation between x and y. It could be 0, it could be 1, or it could be infinity. And these areas are here. So there is 1 in this area, it is 0 in this area, in green area, and there is also infinity, and this is no-go area. So you cannot enter this area. It is like a border in a billiard. So you cannot penetrate this border. You have, so this border is red. So this is no-go area for variable x. And you do this for all variables, and you get a piecewise constant model where your right-hand sides are just constants in different domains. And you have just to match the trajectories in these domains. So this is how it will work for simple heteroclinic cycle. And in the heteroclinic cycle is just a sequence of straight lines. So, and here I compare this piecewise constant model with the original equations. I don't compare the variables themselves, but I compare the velocities. In the piecewise constant model, so the velocities are constants, like here, and they are at some moments of time, they switch between different regions. And here I show the same velocities in the original equations, how the trajectory approaches heteroclinic cycle. And you can see that initially when you are far from heteroclinic cycle, so the correspondence is rather bad. So here it is more or less smooth oscillations. But in this domain, you see it is very good correspondence between these two, between the model, except maybe for this small domain where it is switching. So in reality, the switching is not instant, but continuous. But this domain, so time intervals, become less and less important if you go further and your period is very large. So then this domain becomes less and less important. So it is, we expect that maybe, so this piecewise constant model really captures properties of the heteroclinic cycle. And now we try to apply it to the coupled cycles. Now the coupling term is somehow a little bit more complex, but also contains these exponentials, and it contains this coupling constant Q, also in exponential form. And you we then also approximated with look on different domains of these variables, and we see I think so. Okay, so there is two wide domains where this quantity is infinite, and one domain where it is zero. So essentially, this coupling in this representation gives only the border, so some corridor within which you can move. So if you take two terms, because x and x1 and x2 are symmetrically coupled, so you get from two such symmetric pictures, you get an available corridor. So where two variables x1 and x2 can move, and if they move here in the middle, so there is no action of coupling, and only there are borders. So if you touch the border, you can go then along the border, or you will be reflected depending on conditions. So the coupling defines a corridor of possible values of coupled variables, and it works only on these borders. Yeah. So this is how piecewise constant model describes coupling between two heteroclinic cycles. And so interesting in this representation is that you can rescale the equations and get rid of this parameter Q, because so it is just defines you a scale of these variables and time, and then it disappears from the equations. So although in real system, we don't have, we have Q as a bifurcation parameter, in the piecewise constant approximation, it just disappears from equations, which in some sense means so that probably this representation really captures the asymptotic limit when Q goes to infinity. And there are only two parameters, alpha and beta, which remain. And so now how we can solve these equations in piecewise constant approximation. Unfortunately, I could not do this analytically because so there is a very complex picture of domains in this 6-dimensional space of variables. But numerically, I somehow implemented this, so checking boundaries which between different domains, and so making straight line trajectories between these boundaries. And here it is a bifurcation diagram, for particular value of beta when I change parameter alpha. And you see so that here in this piecewise constant approximation, so there are some periodic orbits, or say here and here, A and D, and there are two types of chaos. And so just I will illustrate these trajectories so with projections on the planes. So here, for example, a periodic orbit in regime A. You see, so these are, you see different projections. So these are three upper panels are the first cycle. One, all indexes are one. The second cycle is here. And here there are coupled variables. X1 is coupled to X2, Y1 is coupled to Y2, and Z1 is coupled to Z2. And you can see so that the cycle is some kind of, here it is a rectangle, but it has some pieces. It's not fully symmetric, but it is symmetric according to permutation of variables. And here on these pictures, there are these no-go domains. You see, so here this no-go domain is with a dashed line. And here on the coupled system, it's also no-go domain, essentially coupling points are here also shown with dashed line. And you can see, so there are pieces of trajectory which are inside domains, and there are pieces which are exactly on the boundaries. And in particular, coupling is only working here at these two pieces along the cycle, and in all other, it is not just present. So, but you have some kind of synchronized motion in both two heteroclinic cycle. Now, if you go to another periodic orbit, which you observe at large values of alpha, it is very much similar, but you see, so here there is one large cycle here, and there are two orbits here, so it is a kind of 1 to 2 synchronization. So cycle 1 makes one cycle, and heteroclinic cycle 2 makes 2 rotations. And there are really large domains. It is now more symmetric according to permutations, and there is large domains where the coupling takes place. They are according here this no-go boundary. And there are also chaotic regimes. So there is one chaotic regime which is asymmetric. You see, so here a bunch of trajectories. So here there is a coupling in X, coupling in Y, but there is no coupling in Z. So it is essentially, coupling is in the equation, but it never works. And so here it is a mostly interesting symmetric regime of chaos. So this is pieces of trajectory, you see, so there is quite a symmetry both to permutations and to exchange X1 and X2. And for this regime, so we looked more carefully on how we can understand it in this 6-dimensional phase space. And we constructed a Poincare map, just looking on very long trajectory. And so took some Poincare section. So it is and this is projection from this 5-dimensional phase space on some 3-dimensional one. And one can see it is a closed curve. It is a closed curve essentially consisting of linear pieces. And so there are 17 segments, which are straight lines here, and they are closed. So it is topologically a circle. And looking on, so it is looks like a curve, but in fact it is a lot of points here. It is just discrete points. And the map of this circle onto itself, it looks like this. So we parameterize the curve by coordinate along this circle, and we constructed numerically such a Poincare map. It looks like one non-invertible circle map. It has some 6 intervals of monotonicity. It has here these points, so which of course non-smooth, so it should not be smoothness, but it looks like so that this map numerically constructed indeed has everywhere, it is everywhere expanding. So in particular, even this part, which looks like slope is not so large, is larger than 1. And so this somehow suggests so that really chaos is captured by this piecewise linear approximation of the heteroclinic cycles. So with this picture, I conclude. So we showed in the original equations so that chaos appears at more or less arbitrary small coupling. So some quantities like 10 to minus 40. And but this can be understood within piecewise constant dynamics, and where strength of coupling essentially becomes irrelevant. So it should capture asymptotically behavior at very small coupling. And here it's at least in one regime, attractor appears as a closed curve and with a non-invertible expanding map on it. So thank you for your attention.
Thank you for interesting talk. Questions, please. May I ask a question? In the initial statement when we have smooth dynamical systems. We have chaotic dynamics similar to, it's not robust in a sense that we can take parameters when we put into stability windows.
Yeah.
Yeah.
So I constructed also Poincare map here. So at some points, it looks like a non-invertible also circle map, but it is now relatively smooth. So the picture is resembling, I just didn't put it here. It's picture resembling this, but here it is a smooth maximum and here it is a smooth minimum. It is not exactly like this because I took some another parameter. So, but, so we know so that this sign map, sign circle map, it demonstrates maybe chaos in large domains, but periodic orbits are still possible because here in reality you don't have an angle, but you have a smooth minimum and a smooth maximum.
Yes. In the piecewise linear system, we have no smooth minimal or maximal, and here we have a robust chaos.
It appears like this because so you see, so here in this picture, so there is no any window. Yeah, you see, so it's we call this domain. It's but this is due to this piecewise constants of dynamics. So there is tiny regions where it becomes smooth. They are neglected here.
Mm-hmm. Okay.
Sasha, guten Morgen.
Guten Morgen.
Can I see the very first picture, please? I have a historical question. Oh, no, second. Maybe next. Yeah, this one, right. For some reasons, no, yeah, this one, right. For some reasons, I thought that that was due to Guggenheim and Holmes, that construction, right? Am I wrong? Because you said May.
It looks like May and Leonard did it earlier, but I'm not sure.
Okay, great.
I don't remember when Guggenheim and Holmes were, but in many cases, one refers to May and Leonard.
All right.
It's a 75.
Okay, I'll ask you for the reference. I'm curious.
Yeah.
Okay, thanks.
Can I ask a question?
Yeah, sure.
It's just like you mentioned it goes for very small coupling, but the coupling you meant is diffusive. If you change the function, that is, is it really robust or is stability?
I really never tried, but you see, so here for my consideration, it is important that these variables remain between 0 and 1. Otherwise, okay, numeric, so if you change here, for example, just a forcing, so then this variable u1 could be larger than 1, and it is somehow, it's not so much convenient for me. Although I suppose one can consider this numerically, but for the theory, it is easier to have something between 0 and 1.
If it's a cubic, for example, a cube or something like that, it should be the same. Because
I never tried. I never tried. I would expect similarly because you see, so cubic, it means, so if you take logarithm, so essential here, not the variable itself, but its logarithm. If you take any power, it will be just correspond to rescaling of D, effective rescaling. So I don't expect that there will be any dependence if you put here cubic or square, maybe even.
So even though sine function will do maybe then.
Okay, if you take, you see, so it is a logarithm of u is what counts.
Arkady, hello. Well, these pictures on win and lose that you took from movies, that is true? What is this? Win and lose relations within this set of movies.
Okay, I took this from internet. I suppose there is some kind of online games or all together. So people just play this,
Okay.
you know, so there are generalizations, so you can have more than 3. And so this is probably some table game with such rules. But I just looked for a picture for inverse cycle, and this is the only picture in internet I found for this forward and backward rotations. What is this moves are, I don't know.
And with the model, did you try to do one orientation is the same for?
No, this was already studied in the literature, and they found, okay, nothing very exciting, so it's some periodic or quasi-periodic dynamics.
Okay. Mm-hmm.
But for opposite directions, you see it's immediately from very small coupling, you start with chaos. It's somehow, for me, quite remarkable.
Mm-hmm.
Somehow old friends call that winnerless competition, right?
Yes, exactly.
Right.
Okay. Thanks, Arkady, for interesting talk again. And